So, greetings to all of you present for today's discussion. And the topic for discussion today is physical properties. It will be discussed in two parts. One is rheology and the second one is creep and flow. So, before moving on to the topic, the contents of this session will be summarized in this slide, and you will be dealing with so many new terminologies. So, let me introduce the terminologies first. One is rheology, the next one is shear strain, and how any fluid responds to that shear strain. Depending on that response, you have the categories of Newtonian, plastic, pseudoplastic, and dilatant. One another important terminology what we need to discuss in terms of MCQ is thixotropic behavior. This is a frequently asked MCQ where you will be given which type of liquid will exhibit this type of behavior. So you need to know what is that property and which fluid behaves in such way. So first, moving on to the topic, I want you to understand two terminologies first. One is rheology and the second one is viscosity. First, when we describe rheology, here it is mentioned as study of deformation and flow characteristics of matter. So to simplify this definition, whenever you consider matter, whether it can be a solid or a liquid, how does that material deforms when you apply an external stress? So whenever I am giving a stress, how does that material react or respond? That is study of deformation. And also, since there is always a transformation from one phase to another phase, like solid to liquid, so or liquid to solid, whatever the conversion may be, how does the material flows whenever there is a phase transition or whenever there is a phase transformation? So whether the flow of the liquid is better or whether the flow of the liquid is restricted, all these need to be known whenever you use that particular material in the clinics. So this is the definition of rheology. Next comes the definition of viscosity. So whenever the definition of viscosity comes to your mind, you need to know it is always associated with the ability of the fluid to flow. So whenever I tell it as an ability, it is always the inherent quality of the material to restrict your flow. So always your viscosity will hinder or not allow your liquid to flow. So this can be understood with a good example. As you can see here, you have the first picture of water where you have a very good flow, and the second picture of an oil where the flow is little bit restricted. So from the first picture you can understand water is a very thin liquid or less viscous. Oil is a thick liquid or a high viscous liquid. Whenever your viscosity is less, your flow will be good. Whenever your viscosity is high or whenever the liquid is thick, your flow will be less. So viscosity, now what you have understood is, it is the ability of the fluid to restrict within itself from being flown freely. So water is having less viscosity, it will flow freely. Oil is having more viscosity, so it is restricting its flow and it is not flowing freely. You can also see some examples of liquids where you can compare the viscosities. Your water is having less viscosity, medium viscosity is that of an oil, and when you compare honey to oil, it is even more thicker and it has a flow even more lesser than your oil. So now you have understood all these viscosities, rheology, and now I want you to know first of all why you need to study this rheology and viscosity in regards to dentistry. So before moving on to the topic, first when you see this picture, you have an array of clinical techniques demonstrated here. The first picture showing you an impression gun where your impression material is being loaded, and second picture shows you the mixing of dental cement. Third picture shows you the mixing of an impression paste, and the final picture shows you the loading of your alginate into the impression tray before making an impression. So whenever you see the viscosity or the thickness of the material or the consistency of the material is not the same in all the pictures. Here it is different, in your dental cement it is different, in your impression paste it is different, and the consistency of alginate is different. Only when you know or understand the basic rheology and viscosity, you will know what material to be used under which clinical condition whenever you treat a patient. So with this basics, you will be able to select your material whenever you are attending your patient in the clinic, and you will be able to judge for which technique which material has to be used. So this is the sole purpose of this class, for you to understand rheology and viscosity. So now we'll move on to the shear strain. So before moving on to the general topic of shear strain, I would like you to know that why I am stressing the importance of shear strain rather than other forces like compression or tension. See, in dentistry, whenever you manipulate the dental material, like as you see, mixing of a dental cement is shown in this picture, there is no single force or an unidirectional force you apply to that particular material. The force is always multi-directional. Whenever you mix, it is not your force is not exerted in one direction. Your spatula will be moving in such a direction that the force is always acting along many axes. That's why it is always important to study the shear force and shear strain with regards to dentistry rather than other types of forces. So in simple, your compressive force or tensile force is always acting in one direction. Your shear force is nothing but a multidirectional force. Just to simplify the term shear strain, I am telling it as a multidirectional force. Now with this idea in mind, you come to this Newton's law of viscosity. Here in this picture, you can see two surfaces which is shaded as yellow. The bottom surface is fixed and the top surface is moving. You can appreciate that the surface is moving towards the right side. And also the blue shaded area is nothing but the intermediate fluid in between the two surfaces. So exactly the same picture you can compare to that of a dental material, where you can see the glass slab and the spatula as two surfaces, and the dental cement which is being mixed over the fixed glass slab in between. So here the fixed surface is the glass slab, the moving surface is your spatula, and the fluid in between is the dental cement. So whenever you are mixing a dental cement, the amount of force exerted by the spatula over your dental cement is calculated as the shear force, and whenever you want to calculate the shear stress, it is always the shear force divided by the area. Now the area is nothing but the intermediate area which is present between the two surfaces. So here this is the area between your spatula and the glass slab. So shear stress exhibited over any material is force by area. Now the next thing what we need to know is the shear strain. Strain is nothing but what has happened to the material, what strain has been produced within the material. Now when you see this, over the fixed surface, the liquid was first placed initially in this position. Whenever I apply an external force on the right side, you see the shift of the fluid from this position to this position. Instead of a straight line moving like this, it is moving in the direction of the force. Similarly, when you mix a dental cement, you can see the movement of the cement from the fixed base to that of the spatula, and this change in the position from the initial position to the final position because of your movement of the spatula is called as the strain. So the change in the dimension or distance compared to the original position is nothing but your shear strain. So you can simply understand this Newton's law with this example of your mixing of your dental cement. Hope it is clear how your fixed surface and moving surface and your intermediate liquid is being compared to that of your fixed glass slab, your moving spatula, and your dental cement in between. The change in your dimension of the fluid, like how it is tracking towards the right side. Here your dental cement is also being mixed and it is changing its shape and original length. Hope you are clear with the shear strain. With this, I am moving on to the So depending on how your fluid reacts with the external shear force, you have four different categories: your Newtonian, your plastic, pseudoplastic, and dilatant. Whenever I want to describe or compare all these types of fluid, I want you to particularly understand the individual graph before moving on to the combination graph. First, when you see the Newtonian type of liquids and when you plot the shear stress and the shear rate over the y and x axis, you can see that the graph is always linear for Newtonian. The viscosity remains unchanged, or there is no change in the viscosity whenever you apply an external shear stress in terms of Newtonian fluids. Whereas when you move on to the pseudoplastic, you can see that the graph is concave. Whenever there is a increase in the stress, the liquid starts to thin, or it is called as shear thinning. Whenever a shear force is increased, your material becomes thin and it flows freely when compared to that of the initial position. Your dilatant is nothing but exact opposite of your pseudoplastic, which is called as shear thickening. Here, whenever you increase the shear stress, your material thickens, and one can see that as the shear stress increases, the viscosity also increases. Now you can come to the combination graph, where you can compare the Newtonian and the non-Newtonian fluids, that is your dilatant and pseudoplastic, with the linear graph of Newtonian in a single graph, and also a special mention to plastic type of fluids. Here all your Newtonian, pseudoplastic and dilatant will have your viscosity graph from the starting point itself, whereas your plastic fluids, which is a special category, will not have change in shape until one particular point called as yield point. This particular point in the y-axis is called as yield point because until that point there will be no change in the shape or viscosity. Whereas from that point, if you apply even more stress, there will be a change in the viscosity of that particular fluid, and that's why those type of fluids are called as plastic. With this general introduction, we will move on to each type of fluids. Now, first is your Newtonian fluids. As you can see in this picture, the examples of Newtonian fluids, what we use in your day-to-day life is your water, your olive oil, your mercury, your ethyl alcohol, milk, honey, everything. So what we need to understand from this picture is that these fluids, regardless of whatever external shear stress you apply, will have a constant viscosity at all the times. It doesn't change its viscosity in response to the external shear stress. So that is the thing what you need to keep in mind. So your next type of material is plastic. So as I mentioned earlier, your plastic materials until it reaches your yield point will not change its viscosity. So the point at which your shear stress will produce a shear strain is called is the yield point. So the example what we use in your day-to-day life is your toothpaste, which is being squeezed out from your toothpaste chamber in order to reach the brush. So until you apply an external stress at the yield point, your toothpaste cannot be squeezed out to your toothbrush. Similarly, in dentistry, what type of material is categorized as plastic is your zinc oxide impression paste. Your viscosity of this particular zinc oxide eugenol impression paste will remain the same when you start the mixing of that particular material. Once it reaches the yield point, your material starts to become rigid and it stops becoming rigid or plastic at the end of the set of the material, and that's why the material is termed as plastic. Initial mixing will have the same consistency as that of your base and catalyst paste, and only when it reaches your yield point your material will start to set and become plastic or rigid or brittle. Next property is pseudoplasticity. What is the meaning of pseudoplasticity? I always want you to remember the word shear thinning whenever you remember pseudoplasticity. As I have mentioned in the initial graph, you can consider the example of your ketchup bottle, where the ketchup within the bottle is slightly thicker when you compare to that of the ketchup which is being dropped in the plate. So whenever you shake the bottle, you apply an external shear stress to the bottle, and that causes the ketchup to become thin and freely flow outside the nozzle and reach the plate. Whereas the ketchup which is present within the ketchup bottle is slightly thicker or more viscous when compared to the ketchup which is dropped in the plate. The external shear force causes the material to become thin and flow more freely when compared to the ketchup which is present within the bottle. The same can be applied to your dental material. For example, you have a material called monophase impression material where one single material can be used in two consistencies. You can also use the material like this as a heavy bodied material in an impression tray. At the same time, when you put the material in a syringe and when you hit the plunger, the shear force exerted from the plunger in the syringe will squeeze the material, and one can see how the material flows freely when it is incorporated in a syringe and a shear force is exerted with the help of the plunger. The same material can be used as a heavy bodied material in the tray as well as a free flowing material in the syringe. So you can remember this ketchup example for pseudoplastic, and this type of behavior is called as thixotrophicity. So the MCQ what they will ask is what type of liquids will exhibit this thixotrophic behavior or pseudoplastic behavior or a shear thinning behavior. So all this comes under the category of pseudoplastic fluids where the fluid will be initially thicker and application of external shear force will thin the fluid and the fluid will have more free flow or the viscosity will become less. So the next type of fluid what we are about to discuss is your dilatant. So this is the last type of fluid. In contrary to your pseudoplastic, here on applying shear force, the fluid will thicken. In pseudoplastic, your fluid will thin out. We don't find many day-to-day examples for your dilatant. So I have given the picture of a laboratory example where the person is mixing cornstarch in water. On mixing of your cornstarch and application of external shear force, the mass will thicken. And whenever you stop mixing, the cornstarch water mix will be fluid. So application of force is thickening your mixture and reduction of your force will thin out your mixture. So that is an example of dilatant. The same property is applicable to few impression materials like alginate and elastomeric impressions, where on start of mix and application of shear force, your material will start to thicken. Initially, the material will be flowing freely and record the impression. Once the process of setting starts, your material will become thicker, and even though you apply a shear force to the impression tray and slightly jerk the impression tray, your material will not freely flow or freely move like your pseudoplastic. Here, on jerking, your material will be thickened and it will allow you to freely remove your impression tray from the patient's mouth and you can record a good impression. So it is this property of the impression material which is allowing you to remove the impression material quite thick whenever the external force is being applied, and this is called as the dilatant property where the shear force will cause thickening of the material and allow good retrieval of the tray. So you need to understand, see how subjectively the quality or property of different fluids is being applied in dentistry, and you need to understand the clinical technique before we choose any type of impression material or any type of material in that case for particular patient. Only when you know the flow characteristics and properties of rheology, you will be able to select different techniques and different viscosities of material for that particular patient. So with this, we come to the end, and the most frequently asked questions include your rheology, the graph of Newtonian pseudoplastic dilatant, and also your thixotropic property. So with this, you can post your doubts in this QR code, and thank you for your patient listening.